So now we're in chapter 48 of my book, and as I mentioned earlier, the book has 51 lessons, and this video is going to have about 51 lessons also. So that gives you a really good idea that we're pretty much finished, and as I note right here, I could right now turn you over to the Zio and Cats Effect websites and their documentation, and I think you'd actually do pretty well. But instead of doing that just yet, I want to help you out a little bit more. And the first thing I want to say is that before you're 100% ready for a Zio, it'll help to look at an IO. And in this paragraph here, I have a bit of a mistake. I note that in the earlier days of Haskell, some really smart people were trying to figure out how to handle I/O in a pure way, and indeed they were. But what I didn't do there was give credit to the proper person. So I wrote this on my website. There is a man named Eugenio Moggi, if I'm saying his name right. And in this 1989 paper that he wrote, he had created or discovered a concept that would have profound effect on functional programming and how functional programmers would handle computational effects. And as I should note right up here, I worked with ChatGPT to get the information that's shown below here. So I kept trying to work with ChatGPT to simplify this as much as possible, and this is what we came down to. And this is all important. Everything on this page is important because it leads up to this concept of I/O, or what is an I/O. So the first thing to say is that he used category theory to provide a formal and mathematical framework for understanding and describing computational effects. And to that end, I have another document here, and I'm just going to show the name of this author because I'm afraid I'd butcher it if I tried to say it. But this is from a book, and you can see the title up here. It was Category Theory for Programmers, and this was the Scala edition of that. So in this sentence over here, when it talks about providing a formal and mathematical framework for understanding and describing computational effects, that's described pretty well over here in this book. So in the book over here, the author lists these problems, and he mentions that he copied them from the paper by Eugenio Moggi. And he said all of these problems traditionally had to be solved by abandoning the purity of functions. And these problems were broken into these categories here. So they have partiality, that's computations that may not terminate; non-determinism, computations that may return many results. And this might be thought of as a stream or a lazy list in Scala. Side effects, and this has everything to do with input-output, as you see right here. Exceptions, continuations, and then again, interactive input and output here. And so far, we've kind of focused on these here, the interactive output, interactive input, exceptions, and side effects. But the importance of Moggi's work is that he discovered this way that we don't have to abandon the purity of functions. And of course, that has to do with what we now call the I/O type and monads. So coming back over here, Moggi introduced monads as a powerful abstraction, and that is for handling computational effects in what's considered a pure and compositional way. And monads give us this ability, and they give us this ability to encapsulate side effects and impure operations within a pure functional programming language. And the way he did this, as described here, he separated the description of a computation from the actual execution. And when we get into Zio, you'll see that's exactly how this works. When you create an instance of a Zio, which again is a type of an I/O, you'll see that all you're doing is creating a description of a computation. Nothing actually happens when you create an instance of a Zio. And the actual execution is deferred until sometime later when your code is actually run. And this is really cool when you get to see it in practice. And there's a couple of other important points here. So he formalized various computational effects, and what I've written here about these effects is the same type of information that you'll see over here in this book. And at the time, what they had was each type of effect could be represented by a specific monad. And then that was cool because it made it easier to reason about and compose programs with multiple effects. And you'll see composition is really important. And indeed, what you find in the book over here is that the author wrote that composition is at the very root of category theory, and in fact, it's part of the definition of a category itself. And so he states here that he would strongly argue that composition is the essence of programming, and composition is simply the matter of combining or composing multiple functions together to solve larger problems. So if you have one small function here, another small function here, and another one down here, composition is just a way of combining those together to solve larger problems. And you'll see what I mean as we get into the ZEO examples. And again, monads offer a means to sequence and combine computations, which is kind of what I just discussed. But what they do is let us do that with different effects, which is really cool. And while we're doing this, we can maintain the things that we want, which include referential transparency and predictability. So as I scroll up here, we can see that Mogi's work on monads had a significant impact on Haskell, and all of that led up to the work in the Scala functional programming libraries like ZEO and Cat's Effect. And finally, down here, I kept this line because I really liked it. And it states basically that monads provide a structured and principled approach for us to deal with side effects while maintaining the purity and safety of functional programming languages, like the work that we want to do in Scala. And that was some theory. And what happened in practical terms is that they invented a concept called this IO type. And for us, just to start with it, you can think of it as being just like try or either. And it's this type that you want to use whenever you communicate with the outside world, or more generally, when you run any other side effect. So anywhere that I had function signatures that look like this with try or either, conceptually what happens is you really just replace those with an IO, or what we're going to do is replace them with a ZEO. And that is a slight oversimplification, but in my much larger book, Functional Programming Simplified, I do show how to write an IO class and then how to use it inside of for expressions, just like we use try and either in this video series. Lastly, there are 3 keys about IO types, and the first one is that they were created as a way to let you reason about your code that has side effects. Secondly, if I haven't mentioned this before in this series, you cannot mix option, try, and either types inside of for expressions. So what I mean by that is you can't have an option type in the first line, then a try type in the second line, and then an either type in the third line inside of a for expression. You can't do that just mathematically, and in terms of types, you just cannot mix those together. But what you can do is you can mix as many IOs in there as you need to. And as I note, to help with that item, with that problem in number 2, IO types are like try and either, but they're like on steroids. They are much more powerful than those types, and they have tons of built-in features. And as I note inside the parentheses here, you could write a type like try or either in less than a page of Scala code, but IO types have been developed over many years of efforts, and I mean many people working on these for many years. So if it takes something like 10 or 20 lines of code to write try or either, you can imagine multiplying that by thousands of times of effort to create these IO types. So given that background, we're going to talk about IO types a little bit and how it is that they help you reason about your code.